Hello, and welcome to the Area Research Committee webinar. My name is Christine Perret. I'm the chair of the Area Research Committee, and I'm very pleased to have you with me today for an exciting webinar on the subject of optical radiation, the assessment of hazards due to optical radiation when using AR and VR displays. This is going to be presented to us by a researcher who will tell you a little bit more about his laboratory and the Polish Institute for Labor Protection. First of all, I want to thank you again for being here and remind you that you are in listen-only mode. However, in your GoToWebinar control panel, you have a questions section widget, and I invite everyone to enter your questions in that tool, and I'll take those after the presentation. But first, let you know what to expect from today's webinar. I'll just have a short introduction to the area. Then we will have a presentation by Mariusz Wiselka, and then we'll have a time for questions and discussions with you. So for those of you who might be unfamiliar or need a reminder on the AR for Enterprise Alliance, we are a global nonprofit organization composed of 3 segments, which we think reflect the global enterprise AR ecosystem. The segment on the top of the pyramid are the enterprises who plan or who are already using augmented reality for productivity, enhancing performance, reducing loss, and reducing risk. They're in all different stages of their evolution and the introduction of augmented reality. And they partner with and collaborate in the context of area programs, the other 2 segments of our ecosystem, the providers of technologies, the AR software, hardware, and services that enable augmented reality in these production environments and in the workplace. The providers are highly varied in their size, in their activities, and areas of specialization. We have startups, and we have extremely large industrial companies who you'll be very familiar with. The third segment of the ecosystem in the area are non-commercial entities, and this includes research institutes, academic bodies, universities, and so forth. Now, a variety of organizations that conduct research or outreach and support the ecosystem, both by partnering with enterprises and also by commercializing some of the new technologies they develop in the hardware and software that we have in our companies. So those are the 3 segments, and we work together in what we call the 4 pillars to grow the enterprise AR ecosystem. And we do this by producing quite a lot of thought leadership content. We publish it on our website. We also support publishing in our members' websites if they need that in their intranet. We have webinars, we have podcasts, of course, a blog, social media, and lots of other channels for communicating the ideas and the expertise of our members. We also support networking and collaboration between our members, as well as between members and the larger ecosystem. And that's to really share experiences, explore win-win relationships, and reduce the uncertainty and accelerate the adoption. We found early on, and it's still the case, that there are not enough professionals that are trained in the domain of enterprise augmented reality. And so we have programs to support the training and certification of professionals that will then be qualified to work in your companies and developing products as well as implementing, deploying them in the enterprise. Then the fourth pillar is we operate and support committees that are designed to reduce the barriers to adoption. And these committees range from this research committee, for example, where we run programs on behalf of area members and offer public information, but also the safety committee. There is a device and display security committee. We also have a marketing committee and study the requirements for augmented reality. And we're going to try to reboot our some task forces. We also have an interest group on human factors. So those are ways that we believe we contribute to the growth of the enterprise AR ecosystem. That concludes my my introduction, and I'd now like to invite you to, I'm going to invite Mariusz to to present his slides and share with us the research that he's been doing. Mariusz, the floor is yours. Thank you. I see your slides perfectly. Perfect.
Yes, okay. So thank you very much for this introduction. I would like to say a couple of words about the Central Institute for Labor Protection. So the purpose of our institute is to provide solutions for both enterprises and judicial system in Poland on the field of labor and labor protection in general. So as the Laboratory of Optical Radiation, we are taking part in the research as well as measurement of the optical radiation on the in the companies, in some kind of factories, etc., etc. We are trying to measure, we are trying to provide information for people, how to improve the condition on the workstation, how to improve the condition of people working with some, for example, industry technologies. So when it comes to the presentation itself, it's rather a new thing for us, and I think it will have some information new for you too. Maybe they will be useful also, I hope so. Basically, I would like to share with you what we accomplished, what we were able to make, to build, as well as what we were able to research in terms of the optical radiation emitted from the screens or displays, depending on the system, from different AR and VR solutions. The quick outline. So first, I would like to talk a little bit about what devices we were using. Then I will tell you a little bit about the risk assessments related to blue light hazard and the circadian disruptions. Then we will move to the method of measurements of the optical radiation and the measuring station, measuring stand, as well as measurement conditions. In the end, I will share with you our results, our summary outcomes, and a little bit of ideas and places we can look into the future about this technology. I think the augmented reality devices are primary topic for today's session. I will tell a little bit more about the VR system too, but for now, in our study we used 3 different AR devices. Those were Vuzix Blade, Microsoft HoloLens, the version 1, and Epson Moveiro BT35E. We tried to find the source type installed in every single one of them. Sometimes it might not be as accurate as we wanted, so there are some question marks. We are not always sure if what's installed inside the each device. We also check the resolution and the display area of each display in each glass. This is important for later, so that's why I show it here. The VR devices, those were also 3 different solutions: the Oculus Rift, HTC Vive Pro, and Semicave. First 2 are glasses, Google's systems. Those are the popular one. I think everyone have knowledge about them. And the third one, Semicave, is actually the solution we installed in our laboratories. This is the cave system. So the projection is shown on the 4 walls as seen on the lower panel, the most right picture. Potential risk hazards arising from optical radiation. So today I would like to talk about 2 of those potential hazards. The first one is the blue light photochemical retinal hazard. This is basically the hazard related to too much blue light illuminating retina. Word photochemical in this risk assessment tell us that it's not only we should not only consider the level of the exposure, but it's also important to consider the time of the exposure. So what it means is that we can be exposed to short impulses, but if those impulses are frequent and there are a lot of them during the day, the risk can be still high in some cases. So the range of the exposure, so eye exposure, and the range of this hazard is from 300 to 700 nanometers, mostly in the visible range spectrum of the optical radiation, but the most effective is in the blue light band, and it's from 400 to 500 nanometers. How do we calculate it? Oh, I'm sorry. Oh, okay. So the assessment. So in European Union, the exposure limit values are laid down in the regulation. That's the Directive 2006/25 EU. There are actually 2 parameters to be considered, but for most of the devices, we have to consider the effective radiance. The other one is effective irradiance, but we will not talk about this one. The effective radiance will be used for the most AR systems or VR systems. That's because most of those systems are considered as large sources. Large sources are actually the sources that maybe a short disclaimer here, because I have to say that, okay, there are the regulations that the European Union gave for each country, but each country can put even more restrictive regulations within their country. So, for example, if we have here a value 100, in some countries it can be 50. They can do this. But going back to the main topic, the large sources, which I was talking about, are the sources which are seen by our eye as larger than 11 milliradians. And this is because of the optics of our eye. So the focal length of the eye, as seen on the picture in the middle, and the retinal spot size decide how how large can this angle be. If the source is larger than 11 milliradians, this is always considered a large source. If this value is lower than 11 milliradians, the source is considered a small source. The exposure values are not the only thing to consider, because the exposure time is also important. The regulation said that until we exceed the time of exposure more than 10,000 seconds, we have to calculate this formula here. For effective radiance, LB equals 10 to power 6 divided by the time. If the value of time exceeds 10,000, this value is constant, becomes constant, and is around is 100 watts per meter per steradian. The second risk assessment, the second hazard included in today's presentation, is non-visual effects which are not regulated by European Union. I think there are no country yet that actually set those regulations regarding these effects. But this problem is lately really important, really really researched. So there are more and more presentations about this effects in the publications, in the presentations. So why is it important? There are actually effects that involves light, but doesn't involve seeing as we know it. In short, a light has an impact on our day-night cycle, but we don't have to be able to see to actually be affected by this this phenomena. First things, we have to take into consideration that light is important, and we evolved around the day-night cycles on the Earth. So if we measure the spectrum, there is more blue light, for example, in the early stages of the day, so in the morning, and there is more and more red light as we move on into the noon and then into the evening. When we wake up, what's happening is when we wake up, we expect to actually be exposed to the blue light in general. So our system can, our circadian system can actually start suppressing the melatonin in our organism, so we can wake up and wake up faster and be ready to start our day. In the night, the process reverses, and we should be expecting lower and lower amounts of blue light, and in this process we should have more and more melatonin in our system. So why actually we are dealing with this problem? Because there are basically health hazards related to the circadian rhythm disruptions. If we are maintaining our healthy clock, healthy circadian rhythm, it will regulate our sleep, our alertness during the day, muscle and reaction time, as well as release of insulin, for example, blood pressure, but also liver function and cardiovascular ability and muscle strength. If we happen to disrupt this clock, there will start to there will be problems with our, for example, sleep quality. There might happen to be depression or mental health problems, muscle dysfunction, cardiovascular diseases, insulin resistance, or even diabetes. and other symptoms that actually affects our life. And in the worst case scenario, there are also researchers that state that it can even lead to the cancer. How we can measure and how to assess the impact of the light on the circadian rhythm? There are two commonly used measures that can describe lighting and the effects of this lighting on the human body. The first one is equivalent melanopic lux. This is based on the melanopsin response. The melanopsin is the pigmentation in our eyes that doesn't react with the neuron systems as for example our retina does. So the melanopsin response to light is based on the studies on the animal. We can see that the relative efficiency of this parameter is also around the blue light. So the maximum is expected to be around the 490 nanometers, and it's gradually decreased to about 0 in the red spectrum of the light. The second one is the circadian stimulus, and it's based on the melatonin suppression, and those studies are based on studies with humans. And the CS parameter is commonly used with other parameter, which is CLA, which is seen on this picture down below on the left. And as we can see, this is non-linear relation between those two parameters. The values of the CS is within the band from 0.1 to 0.7 and can vary. So the different irradiations values can lead to different CS values depending on the spectral distribution of the light we are measuring. Some recommendations: so CS parameters during the light should exceed the 0.3, and if the evening shouldn't exceed the value of 0.15. The EML parameter, equivalent melanopic lux, should exceed 115 lux during the day and shouldn't exceed during the evening and the night the value of 50 lux. I'm sorry, not this one. So how we measured, what we have done, what we were measuring, and how we gathered the information about the optical radiation emitted by the AR and VR displays. So we, in each and every system, in each and every VR and AR solution, we actually displayed those 7 pictures. The most important ones are the white, the cyan, the blue one, and actually the cyan and white checkerboard, with the black and white checkerboard being here as the simulation of normal text displayed on the screen. The checkerboard is easier than to scale compared to the normal text, because there can be different types of the software which can then display the text on the AR or VR glasses or solution. So measuring stand, this is our mannequin. This mannequin was prepared to host 2 independent channels to measure, in case some glasses might not have displays in both glasses, or there can be only one, so we have to change the position of the probe. So the probe we are using is seen here. This is a metal pipe that's actually installed in the back of our mannequin, and the assembled station is shown on this image. Actually, we are using the right channel we could only measure one channel at the time, so we have to make an assumption that both displays were actually displaying in the same way if there happen to be two displays in AR glasses during the measurement. We were using the spectroradiometer. The results were based on the spectral measurements, and we were measuring the irradiance. The spectroradiometer was GL Spectis 50. It's produced by GL Optic, the company we are working with. We have a wider band than we were actually needed for this this study. We can measure the band of from 200 to 1050 nanometers. So with some additional probes, we can actually measure or also detect the UV radiation in case it's needed. Measurement conditions, we were trying to always reach the ambient light near 0 lux, so it was complete darkness. In two cases, we had to turn on the light because, for example, Microsoft HoloLens requires around 1 or 1.5 lux, depending on the environment it's in order to work properly. So if we want to measure anything, we had to provide some ambient light, but this ambient light was later on discarded from the actual results. So the computer screen were, of course, turned off, not to disrupt the measurement. As I said, it was assumed that if there are two displays in glasses, we measure only one because we assume that both displays display in the very same way. Also, we always checked if the measuring field was fully illuminated by the glasses. So I'm not sure if you are able to see this, but this mannequin was actually we were using the the right channel, and we were trying to always illuminate the measuring area fully. About the outcomes and results. First, I would like to say that the blue light hazard, the risk with blue light hazard, there is actually no risk associated with photochemical hazards to the retina, based on our measurement, based on the systems we were testing during our studies. The outcomes are in both irradiance and radiance, so we have to calculate from irradiance into radiance separately for each device. When it comes to the results, we can say that they are very, very safe. We are far from the exposure limit values. The highest detected radiation was around 100 times lower than the exposure limit values. But however, there is also one thing to notice here, because as you can see, the highest measured value by the spectroradiometer was actually for Vuzix Blade AR solution. But after recalculation, we saw that actually the highest values we can compare to the regulations are for the Epson BT35T. That's because the size of the display installed in those two devices. The Vuzix Blade has relatively large display, and the Epson has relatively small display. This into the relation of how these values are calculated, turned out that the smaller the display, the higher the values we can expect, actually, which can lead to the conclusion that we cannot infinitely miniaturize our displays, because it can in future lead to the problems with the blue light hazard and this and prove that there is actually a risk associated with photochemical hazards if we use too small displays. Other measurement results, impact on the circadian rhythm. This is actually into slides. The first table consists of the CS values calculated for all images presented in each of the solution. Here we can note that some devices might be wise to use during the day only. That's because the values we are actually measuring exceeds or sometimes exceeds the value of 0.15 of CS value. We should also note that the Vuzix blade, in case it's only displays white screen, white image, might be used as only source of light during the day without the ambient light. What's important also to notice here is that for all AR systems, they will work with some ambient light in the near vicinity of the user. So there will be some lighting systems, there might be some screens, there might be some other light sources. All these parameters, all this light will be added and only calculated after it's all added. So all these results are for only the AR system and VR system without any ambient light. So if we add some more, there might be a problem. There might be some risk, some impact on the circadian rhythm. Also, one thing to note: the white or blue or cyan only displayed on the any solution is not something common. It's actually the worst case scenario. So if we want to test the actual solution, we would have to display something that the user will actually work with commonly. So some kind of application, some kind of maybe menu screen, or, well, depending on the work it will be used for. The other values are the equivalent melanopic lux values. Here the measurement results are somehow similar. There are more restrictive results regarding the white and cyan color, as well as cyan and white checkboard. Some values exceed the 50 lux that shouldn't be exceeded during the night or the evening, and some of them are not enough, for example, as the lone solution in the daytime or in the morning. So only, again, the Vuzix blade, while displaying the white image only, can be used as the only solution during the morning that can provide this boost, this boost to our melanopsin to stop the to actually suppress the melatonin in our body. In the summary and the conclusion, I have actually the 3 points here to note. There is no photochemical risk to the retina. So as I said previously, there is for now no hazard. There is no blue light hazard. So I think all the solutions are pretty safe in this matter. So the regulations should be okay with this. The potential impact on the circadian rhythm disturbances when some of the tested devices are used in the evening and the night. This is related to the last two tables. Some devices should not be used, for example, before we are going to sleep. They might have some impact, so in the long run, it's not advised to use them just before the sleep, or in some cases, maybe even just in the evening, we should put them off. So we would like to test some large variation of devices in terms of the display method, the radiation spectrum, and the angular size of the display image, because they can significantly affect the measured parameters of the optical radiation, and it can impact the radiation hazard assessment in the long run. So the more we test, the more we can actually say about which devices can be better, which devices can pose less harmful, can be less harmful, let's say like this. So thank you for your attention for my presentation. That's all today. Thank you very much.
Thank you very much, Mariusz. That was very, very interesting. It's fascinating. Do you know of any other laboratories or studies that are going on at this time or that have been conducted on these topics in the past?
So the studies or the topics, I think we are first, because I haven't found anything when I was preparing for this study. There wasn't actually any literature, any publications I can find that could say something about the large variety of devices tested in one study. So there were some tests, there were some studies for one or two solutions, one or two devices, but nothing major was found. Maybe it changed like in last 4 or 5 months. I haven't checked, to be honest. So there might be some new information.
Well, it sounds like you're really at the forefront of the field. And I believe that this is an important domain for designers of devices, but also those who are taking care of the safety and the well-being of employees. Are you going to look at any other hazards related to the optical radiation? Have you considered other than the melatonin production, or?
Yes. Okay. So actually, we are prepared right now for measurement or measuring actually other risks, potential risk. Maybe some enterprises will go, or manufacturers will go this way. When it comes to the displays, we want to measure, or we also can measure the potential risk of the lasers. So if someone would like to install some kind of laser solution as the light source inside these glasses, we are prepared to measure this also. And as well, we can measure the UV radiation, because our spectroradiometer can measure it, and we have the probes to do it. The UV radiation is something we were considering to measure at first, but there are actually no light sources that may produce this the radiation installed inside the VR or AR devices right now. Maybe in the future someone will come up with something like this, and we can check if it's safe, right? But for now, I haven't found any. So we measured it for these devices we used in the study, yes, but we haven't found anything. So both in the UV radiation and the laser radiation, there was just no signal. So yeah.
Right. And since you were studying this in the very highly controlled environment that you have in your lab, I wonder if you could study and compare the effects of using the devices outdoors? Because when the conditions outdoor are very bright, then the display can be much stronger, much brighter in order to compensate for the bright outdoor environment.
Yes, I am aware of that because the potentially there are solutions for more advanced, for example, advanced AR solutions that can adapt to the environment and the lighting of environment, make the screen brighter or less bright or darker. But there is this problem because we can only assume that, or we can only compare our measurement with any regulation without the natural lighting, so without our sun. So if we are going for some measurement, for example, on the in some factory or in some workstation where there are some lighting system installed, we have to make our measurement during the night because we can't add the we are actually testing the solution itself or how it works on its own, not in the lighting provided by our natural star, by our star, right? Mm-hmm. I'm not sure if that's understandable.
Well, I mean, it is difficult to use these systems in very bright environments. Okay. There's a question from one of our attendees. Mm-hmm. So, you studied the impact of these systems on melatonin circadian rhythm. Can you compare how these impact the system, the human system? Compare these glasses to other light sources that could be used at night, like your computer or your smartphone. Okay. Can you discuss that a little bit?
Yes, I can. Maybe starting from the beginning, because the circadian rhythm disruption and all the metrics I presented are actually only used right now for the artificial lighting systems we have installed in our rooms. So they are not really used for the displays yet, but I hope they will be adapted to this as well. So both equivalent melanopic lux and the circadian stimulus I was talking about actually vary between the different things we measure. For example, as from my personal experience, I know that some systems, for example, personal computer systems, have an option right now that any user can activate at any time that can lower the blue part of RGB from the display. So at some point when you are looking at your display, for example, in the evening, you can notice that it's become more reddish and it's happening automatically at the set time, or you can change it this time as you basically please. Just go to the option and change it. Also, your smartphones, I think both an Android and iOS, has this option probably available, but I don't know from which version. It wasn't, I think it's not a recent, maybe a 3-year-old version of the Android or iOS should have this option too, but sadly we haven't yet compared those screens, those systems like cell phone screen or computer screen to the AR or VR solution. This is actually a very good idea to do this comparison and see how it turned out.
Mm-hmm. Very good. Well, people really enjoyed your presentation. We wish you the best in the continuation of your research.
Thank you very much.
We think that could be, look forward to hearing more from you and about your study. And if there are other candidates that are working in your laboratory, we'd welcome hearing from them. That's the end of today's webinar. Thank you, everybody, for your participation and your attention. Thank you, Mariusz, for a great presentation. Really appreciate it.
Thank you very much.
Okay. Bye-bye, everyone.
Goodbye.